Good evening from rainy Cheshire. We're not well on that, because last night we had a television first with this live view of the Northern Lights in Norway.
But we're not settling for that. Tonight we're sending our cameras up to 30,000 feet to get away from the clouds, the light pollution and any moisture in the air to get the clearest possible view.
And there's a lot of moisture in the air.
There is.
It's the clearest possible view, unless that is you have flown through the aurora, as one of our guests tonight has. We've got the former commander of the ISS and one of the first crew ever to fly in an Apollo spacecraft.
I'm Brian Cox, he's Darragh O'Brien, and this is Stargazing Live. Tonight's show is all about space exploration, and I am genuinely excited. I've been inside all day, haven't I?
For good reason, I think. For very good reason.
Really, because two of my heroes are in the building. From the very first crew ever to fly an Apollo spacecraft 46 years ago, Apollo 7's Colonel Walter Cunningham is here.
And the former commander of the International Space Station and the Space Shuttle astronaut, Commander Chris Hadfield. There they are there, relaxing, as only astronauts can.
That is how to relax, isn't it? If I could only do that.
I know. We've not earned the right to relax like that. If you've got a question about any of this, for those men in particular, or for any things we'll be covering tonight, send them to us. The addresses are on the screen right now.
You know, I've just been distracted horribly by that.
By the fabulous use.
Why is that in my
field
field of view?
Magical hollow ball. It's glorious.
I should say that, so the Lovell telescope, you see it every night. It's usually in that beautiful position for us because it looks nice. But what you'll see over the show is it's going to move. It's going to do some observing, and that's because of some of the candidate gravitational lenses that you found last night. I'm not going to say any more. We're going to talk about it tomorrow. But one of them is so interesting that the Lovell is going to go and image it during the show, so you'll see it side on. Real science being done.
Stuff you've done is making us turn that as well as that. Photos you sent in. Photos you sent in of the aurora already.
Oh, yeah. So this is a photograph from last night. We saw the beautiful aurora in Norway. This is from Caithness in Scotland. Stuart Watt took this picture last night of aurora over a Scottish landscape. And another one from Scotland here, Loch Stemster. Gordon Mackey took that one again last night. Beautiful pictures.
And we're expecting more, aren't we?
Well, there's something very interesting happened, actually, just before we came on air. To do with this sunspot group. It's a big sunspot group, beautifully named AR 1944 and AR 1946. But these, you could fit about 7 planet Earths in this area. Extremely active region on the sun. And if we look at this video, then last night, about 6 p.m, just before we went on air, the Earth is about here to orientate. This is like one of the stereo spacecraft, by the way, that's kind of at right angles to the sun. So we're looking onto the sun, the Earth is here. If we play the video, about 6:30 last night, just before we went on air, that happened. Wow. That is a big coronal mass ejection, CME. It's actually called an X1.2 event. X are the biggest, most powerful events. So that is a big flux of solar wind on its way to us now.
And when should it get to us?
It's going to hit us just after midnight tonight. It's a very big event. It actually delayed the launch of a supply spacecraft to the ISS, the International Space Station, today. So that could have a big effect on the aurora.
Probably will, because we showed you last night here on the Hollow Ball. We showed you.
Your face is gone.
Yes, I know, but it'll be back. This obviously is our globe. There's Africa, there's Europe, there we are there. And if we tilt down, so you can see the Arctic Circle. Now, normally the aurora will be the golden circle here. We believe, because of the amount of stuff that's been thrown out by that coronal mass ejection, that it could extend down as far as the blue area here. And you can see there, I hope, that extends over the British Isles and Ireland, which means that we could get good aurora photographs from you, 12:38 tonight, much more southerly than we normally get.
It's certainly going to be worth your while. If it's clear in Scotland, well worth your while. Really, as far north as Manchester, even as far south, you know, possibly down towards London. It's unlikely, but I really recommend, if it's clear, we're going to show you how to take these photographs later, actually. If it's clear, it's worth a look after midnight tonight, because this is a powerful CME that's on its way. It's like we planned it. I'd like to say we planned it.
Perfectly timed.
Anyway, meanwhile, we're going to take you on an aurora hunt from your own armchair.
Tonight, we've set Liz the task of taking her cameras to an even better vantage point. Liz, what are you planning?
Tonight, on our mission to try and get you the best view of an aurora, we're trying something that's never been done before. We're going aurora hunting from this aircraft live on television. We're going to eliminate the risk of having our view obscured by cloud cover and light pollution, and very shortly we'll be flying at an altitude of 30,000 feet above Norway on the hunt for the aurora borealis. See you soon.
Fantastic, well done, Liz. Look, the moon. I want one of these things.
A moon or a ball?
Not the moon. Just this. The hollow ball is fantastic. Good luck, Liz. We'll be catching up with her again above the clouds in a while. Meanwhile, back down to earth after a gloriously clear night in Norfolk yesterday. Mark has returned to Jodrell to join us in the rain.
Yes, it was wonderful weather, Dara, in Norfolk, but I have seemed to have brought a load of rain here with me. But later on, I'll be showing you how you can spot satellites in space with the naked eye, and even the International Space Station as it passes overhead. Now, astronomy is an incredibly sociable activity. It really brings people together, and that's been definitely true this week. There have been star parties across the country, and this is the scene of a massive star spectacular in Portsmouth with over 5,000 people in attendance. They had telescopes, they had demonstrations, stage acts, and even a solar system. Now, there are more star parties to come, so you can check our website for details and find one near you. And if you're going to one tomorrow night, look out for me and the crew. Now it's back to the guys in the studio.
So use that same web address to get your aurora photographs in for us. We're very excited to see how southerly this could actually get. Now, in a moment, we're going to meet the first of our special guests. But before that, let's take a look at how far we've come, or perhaps more accurately, how far we've gone into space over the last few decades.
You are hearing the actual signals transmitted by the Earth-circling satellite, one of the great scientific feats of the age.
When it comes to pinpointing the moment we first made it to space, a small polished sphere called Sputnik often gets the credit. But Sputnik was actually just the first item into orbit. In truth, we'd reached space over a decade earlier. Our first trip out of this world certainly wasn't one to be celebrated. A Nazi V-2 rocket hurtled out over 62 miles above the Earth's surface and started the space age with a deadly bang. It was 1961 before we could cheer our first real-life spaceman, Yuri Gagarin.
As he looked down on the Earth, on the loneliness of space, controlling the pitch and roll of the ship.
Gagarin made it 203 miles from the Earth's surface and returned a hero. But when you think our planet is about 8,000 miles across, in terms of distance, this was a tiny step for mankind. The giant leap came 8 years later.
We choose to go to the moon because that goal will serve to organize and measure the best of our energies and skills.
On July 16, 1969, Apollo 11 blasted off from Kennedy Space Center. 4 days later, Neil Armstrong made history.
It's one small step for man, one giant leap for mankind.
But Neil, Buzz and Michael don't hold the distance record. 3 astronauts just beat them, but not exactly on purpose.
We're reading 0 into pressure in fuel cell 1.
When Apollo 13 aborted its lunar landing, its trajectory around the moon took the crew further from Earth than anyone had ever been before or has been since. But we'll forgive the crew for having other things on their mind at the time. Impressive stuff from our spacemen. But they really only managed local trips compared to our robots in space. We've successfully landed robots on 2 planets. Our nearest neighbour Venus and the red planet Mars, which even at its closest point is a whopping 34 million miles from Earth. Russia got there first with the Mars 3 probe, but NASA's Opportunity rover went one step further. It landed in 2004, then drove around the surface a full 22 miles, making it our top planetary explorer. But some robot explorers never end their journeys. We've sent dozens of probes throughout the solar system. Some spend their lives orbiting the sun, while others go on to roam the planetary systems. Cassini is almost 1 billion miles from Earth. But for the real long-haul trophy, there can be only one winner. In 1977, the probe Voyager 1 blasted off on a grand tour of the planets. But it was the little probe that wouldn't stop. After diligently visiting Jupiter and Saturn, it has just kept going for almost 4 decades. In August last year, it passed another milestone for mankind, as it became the first man-made object to enter interstellar space.
Well, it's a great pleasure to have Commander Chris Hadfield with us now, Commander of the International Space Station, space veteran. Chris, welcome to the show.
Gentlemen, thank you very much.
You, as I did, as many of us did, grew up with that history that we've just seen. But what was it that made you decide to be part of that history, to become an astronaut?
You know, it's wonderful to see those images because it was on a black and white television watching Neil and Buzz step onto the moon. The reality of that sort of superimposed with the science fiction of the 2001 A Space Odyssey and Star Trek, all of that happening simultaneously, that was incredibly enabling for a 9-year-old boy to see that fantasy can actually come true. And I consciously decided when the night that Neil and Buzz, July 20th, 69, when they walked on the moon, to become an astronaut when I grow up.
But did you think that was going to happen? Because so you went into the Air Force, you became a test pilot. Was that all the plan? It seems to be a plan now.
Yeah, it looks linear now. I had no idea. Canada had no astronaut program, but I recognize that you have to turn yourself into an astronaut if you ever want to become one. And so I go to university and learn to fly through the cadets growing up, and then I decided to join the Air Force, become a fighter pilot and a test pilot. And amazingly enough, in my mid-30s, Canada had an astronaut selection, and I was an astronaut for 21 years after that.
Because you've done 2 shuttle missions and 1 ISS mission which lasted for 6 months. And we have a million questions coming in, all of which essentially boil down to, what is life in space like? How different is it there?
I think it's probably 2 main differences. One is you're weightless the whole time, which is magic. To be able to fly, even something as mundane as clipping your nails becomes different in weightlessness. But the other, maybe the more magnificent part, is that every time you go by the window, you're orbiting around the world every 90 minutes, and the world's turning underneath you, so you see the whole planet over and over again. That combination of the mundane of a haircut combined with weightlessness and the beauty of the world underneath, it was even better than I dreamed it would be when I was 9 years old.
Well, yeah, I hear many astronauts speak of the experience of being in space, and they all say that it changes them. It changes their view of the Earth, it changes their view of themselves. So how did it change you? Because you spent 240 days out in space?
Yeah, about 6 months total over 3 space flights. I didn't have a sudden epiphany or huge change of direction in my life as a result of flying in space. I think it's because of the experience of the people that had gone before. But I think what it really did fundamentally was broaden my own horizons of the world. What I would view growing up as us and them. When you go around the world thousands of times, that line where them begins recedes further and further away until eventually the whole thing just becomes us. You get a sense of oneness that we're kind of all in this together. And that perspective, I did my best to share through the photographs and social media, and it sure had a profound effect, I think, on my own views.
When you spend something like a 6-month tour, for example, on the ISS, is it possible to have a normal day? Are your days 24 hours long? Do you change the rhythm of days?
Oh, you wake up, that watch that's floating there woke me up at 6 o'clock every morning. We'd clean up with a sponge bath, work throughout the day, and then get ready for bed at night. And you can see, you just pull up the sleeping bag so you stay warm. You float next to the wall. You shut off the light in your little sleeping berth, close the doors, and it's the most relaxing sleep you can imagine. You can relax every muscle in your body and just hover inside that sleeping bag until the alarm goes off the next morning at 6 a.m. and wake up.
Is it possible to get a good night's sleep? Not only just physically, it must be rather strange in weightlessness, but I suppose it's a dangerous environment to work, isn't it? You're up there.
Once in a while, you actually hear a meteorite ricochet off the outside of the space station. You hear a thump or a bang or a crack as something runs into the station, and it's a reminder of where you actually are. When you're inside a building, you think you're kind of bulletproof, but when you hear one of those hit, you recognize that you're actually in an aluminum bubble. Yeah. But like anywhere else, you get used to where you are, and you focus on the reality of it. And if things go badly, they're going to go bad in a hurry anyway, so it's not worth fretting
about. So it doesn't really play on the mind. It almost becomes mundane.
It's not mundane. We practice fire alarms. We practice things all the time, immediate reactions. But you can't let the fear of it dominate. You have to focus on the reality of it.
Do you have we got a number of questions in about the aurora, and one of which applies, I think, specifically to you, from Ben Jure, who said, what would happen if you were to physically fly through the aurora? You've done that.
I was outside, I think, on my first spacewalk, and I removed a bunch of thermal covers off of some equipment. And so I was carrying what was, in essence, a big bundle of laundry, and the arm was moving. My feet were locked in the arm, and the arm was moving me around, so I had a long time to wait. So I shut off the lights, let my eyes adjust. I was looking for Australia in the darkness, but instead I saw the southern lights, and we drove not only by them, but through them. And they were underneath me and pouring up at me and rippling for as far as the eye could see. And the colors that are just barely visible there in an image, the upper reds and purples, they're so much more visible, like powerful to the human eye, and the movement of it, it's almost as if it's just pouring and flowing. And to think that it's going on all the time on our planet, and only once in a while are we in a position to really see it. So I told the crew, well, you got to see the southern lights. The arm jerked to a stop, and they shut off all the lights and took pictures of until we drove into the dawn over New Zealand and got back to work again.
It's an incredible existence, and there's so much of it which is so exciting and fascinating. One thing that's always intrigued me was what it'd be like to float weightless through space. And a few weeks ago, I had the best chance I think I'll ever get to find out for myself, as I went on a mission to understand why astronauts are weightless.
We've all seen the footage. Obviously, astronauts float, but it's an easy mistake to presume that the reason they float is because of where they are. That if you just travel 600 kilometers straight up, gravity will somehow recede, so that it has less of a pull on you than it does on Earth. But that's not the case. To demonstrate that, we don't even have to go that far. We can do it using one of these from here. And the flight we're going on today, the one we're piggybacking on, is a research flight. It's filled with scientists and experiments that require weightlessness, but none of us are going into space. Over the next hour or two, this specially modified plane is going to fly up to 30,000 feet and then plummet towards Earth 25 times. And each time, we will all briefly experience weightlessness. I can pretend that this is about the science, but come on, I'm giddy like an 8-year-old child. This is fantastic. As excited as I am, this overgrown roller coaster ride isn't just for fun. It's also one of the ways astronauts train to cope with life in space. We were told to watch out for how disorientating certain parts of this flight can be. That starts before the plane's even taken off, because I've never sat in an airplane which was as stripped out and bare as this. It's essentially like 4 rows of seats and a giant padded room. Something weird is going to happen here. After takeoff, it's time for the scientists to get their experiments set up. And for me to get my head around what really makes astronauts weightless. Even if you go up to where the ISS is, if you climbed a ladder there, gravity's still about 90% of what it is here. If you walked up a ladder and stepped off, you'd fall straight back down again. The key to weightlessness as we see it is in falling, which is what we're about to demonstrate here. At 30,000 feet, the pilot throttles back, plunging us towards Earth in a series of steep arcs. And each time the plane does this, we get a few moments of weightlessness. And the sensation is incredible. Oh, wow. The trouble is, even the most basic tasks, like facing the camera, oh my God, become impossible. And just as suddenly, it's over. But not for long. So what is making us feel weightless? Wow, that is incredible. Okay. It's astonishing. When it does this, it's like all of the weight leaves your body and you float off. And all we're doing is we are free falling towards Earth at the moment, along with the aeroplane. Okay? I should do more pieces of camera like this. Now, hello, how are you? And it's just the same for astronauts in orbit. What's happening in the ISS is they are basically falling towards Earth all the time, constantly. Sorry, where are you? I lost you there for a second, didn't I? And so it feels to them like weightlessness. And we're down. The only difference between us is that I'm falling briefly towards Earth, sorry Ben, while astronauts are falling constantly around the Earth. Let me explain. Imagine an astronaut falling to Earth like me. Give him a push sideways and he'll keep moving sideways as he falls. Push him too hard and he'll head off towards the moon. But push him just right and he'll never get any closer or further away. He'll stay in orbit. Wow. In constant freefall, he'll feel weightless all the time. Whereas for me, the pleasure is painfully short-lived. I'm okay, I'm grand. It's incredibly counterintuitive. I've done a lot of scuba diving. You kick, you naturally kick, but there's nothing to kick against. So you're just a large man in space kicking anything around him. I went careering off at one stage and luckily a scientist broke my fall. But there you go. Whether you're an astronaut in space or just a man in a jumpsuit, it's not a lack of gravity that makes you float. After plummeting to Earth 25 times, I was quite relieved to land. Thank you very much for stuff. Okay, now, 2 things I'm allowed to do now. Firstly, I'm allowed to take my upside-down name tag and put it the right way up, because I'm now an experienced zero-G flyer. But mainly, the most important souvenir I took from that is one empty stick bag. Nearly got me, didn't get me. Strong like bull. Strong like bull. Very proud I am. Very proud of not being ill on that flight. There's a British scientist called Jan who's on it, who we met afterwards and who had a big stain of being ill on himself. But he was so ill, they wrapped him into a ball on the plane, and when it went to zero-G, they picked him up and pushed him down the plane, and he just rolled down to the back of the plane, where they unfurled him and strapped him into a chair. Oh. Is that anything like a zero-G in space?
Briefly, it's similar, but it's not the same. The duration of it. The people that are sick in that airplane don't always get sick in space, and vice versa. It's not a good predictor. It's still the difference maybe between diving into the water and staying floating scuba diving for a long time in the water. One's a transition, one's permanent. They're similar, but not identical.
Well, Chris, thanks for now. We're going to hear a lot more from you later. I'm just going to enjoy playing with your spacesuit glove that you've lent me. It's a Russian spacesuit, isn't it?
It is, yeah, Sokol suit.
Anyway, if you want to see the ISS for yourself, it passes overhead regularly, and Mark is going to tell you how you can find out where it is and how to look at it.
And it is really easy to see the space station. This is an image we've got from the Earth of what the space station looks like to naked eye, and you can see it moving down the screen as the bright light in the centre. But if you want to see it really clearly, you do need a very powerful lens. Now, we were lucky enough to get this fantastic view of the space station with a super zoom lens during the last series of Stargazing Live. You can see the satellites, the solar panels wonderfully on it. Now, you can have a go at spotting the ISS for yourself. All you need is an app on your smartphone. There are several available which tell you when the ISS and other satellites pass overhead. It's really easy to use. Now, the ISS orbits at an altitude of 240 miles and it travels at 17,000 miles per hour. Now, that's a colossal speed, but the speed is actually one of the ways you can tell that you're looking at a satellite and not a shooting star or perhaps an aeroplane. Now, this is what a shooting star looks like. You can see the image of the shooting star as it whizzes across the screen. It's really quick and very fast, and that's how we can tell that it's a shooting star, not the space station. They travel about 150,000 miles per hour, so they're clearly not man-made. They're a few miles up as well, so of course they just whiz across the sky. Now, planes, on the other hand, have flashing lights. You can see in this, you can just detect the flashing lights at the other side, and they tend to move a little bit more steadily across the sky, so they can be mistaken for satellites. Satellites, however, do move at similar speeds to aircraft, and you can see the satellite at the bottom of this image, but they don't flash, and that's the key way of telling if it's an aircraft or it's a satellite. And they can sometimes disappear over the horizon, and sometimes you may even see them gradually vanish, and that's because they've flown into the shadow of the Earth. Now, back to the aurora. Your photos are coming in thick and fast, and there's a wonderful image we've seen from Tony Rees, and that was taken from northern Iceland. You can see the wonderful colours of green and wonderful folds in the display. We've got another wonderful image from JJ Payne that was taken in Tromsø with some really vivid green colours. It looks really quite spectacular. Now, there's a chance of an aurora over the UK tomorrow night, so if you want to try and photograph it, you'll need a DSLR camera on a tripod much like this. You need to set the focus to infinity, the ISO to about 800, set the aperture as wide as possible and try exposures of around 15 seconds. But don't be afraid to experiment with the settings because the aurora can vary in brightness. And try and get some landscape in as well. Now, upload your photos to the website so we can take a look at them. But for now, it's back to Dara and Brian in the studio.
Lovely. That's how Mark says you should photograph an aurora. Let's see how Liz is doing with her challenge. How's it going there, Liz?
Hi, Dara. How are you doing? This is a bit of a TV first. We're transmitting live to you on our aurora hunt, 32,000 feet above northern Norway, above Tromsø. Take a look at our little plane. It's jam-packed full of people and equipment. We've got our specialist low-light cameras, one permanently trained on the night sky, specialist live transmission gear that's allowing us to transmit the aurora footage live. And can I just show you what we're looking at outside our window right now? What do you make of this, guys?
Lovely. Wow, that's very, very impressive.
The thing is, it's difficult to find the words, isn't it, without just standing here going, that's very beautiful.
Nice,
but the interesting thing for me is that it's a completely different view of the aurora. First time on television, of course, but also, you know, it looks different because it's high. I suppose you can see, well, I want to ask, actually, if it's clearer and you can see different colours. So, Liz, can you describe, is it different to what you saw yesterday from the ground?
You know, that's the thing. We're getting a completely different vantage point from up here, of course. And the thing is, it's been snowing non-stop in Tromsø today. You can just about see in those images the cloud cover and then clear sky, beautiful bright starry night, and then the glorious green aurora borealis. Up here, we don't have the problem of light pollution and certainly cloud cover obscuring our view. So as and when this aurora changes tonight, we'll be there to look at it and get you the footage live. Now, with me on this flight is Pete Lawrence, Sky at Night presenter, becoming my best friend, thick and fast, and he's going to be our expert for the next 2 nights. Pete, what do you make of this?
This is fantastic. I mean, it's really dark outside, obviously, but the stars are shining brightly, and that aurora really is the star of the show, excuse the pun. But it's been changing quite a lot as I've been watching it.
It has. Now, you have taken part in, what, over 200 aurora hunts?
Yeah.
Does this have the potential, with your expertise, to change into something more colourful, bigger, brighter, faster, better?
It's a pretty weak aurora at the moment, but it's still very pretty. There's lots of structure in there. And yeah, I think it could build up, or equally it could go away, but I'm really positive about it.
Okay, well, thanks so much for joining us on this flight. Keep your eyes peeled for us. He's going to be our expert eyes, as I mentioned, for the next 2 nights. Now, you know, this vantage point, getting closer to the aurora, not only allows us to admire them, but it also allows scientists to understand them better. In fact, it is even possible to get right inside an aurora, would you believe it? And it's something that scientists here in Norway are doing. This is the island of Andøya on the west coast of Norway in the Arctic Circle. And it's in this remote place that some of the world's leading atmospheric scientists are trying to find out precisely what goes on inside the aurora borealis. Scientists at the Alomar Observatory are employing a number of methods to study the night sky, including firing out lasers to analyse the lower layers of the atmosphere. Now, these lasers can reach a height of 110 kilometres. That's pretty impressive, but it's still not quite high enough to reach the aurorae, to be able to study them properly. To do that, you need some serious space technology. Rockets. Packed with scientific instruments and launched directly into the heart of the aurorae. But rockets like these can only go in one direction, straight up. So an aurora has to pass directly overhead before the team can launch.
The trajectory is predefined by the launcher, What we're doing is we are waiting for, let's say, an auroral arc, and until this is moving in an area where we know the rocket is going through there. So we are waiting for the right conditions.
So essentially, you're waiting for the aurora to come to the rocket?
Yes, yes.
Recent missions have helped the team to discover that the shifting patterns of light in aurorae are caused by charged particles falling in vertical bands just a few meters across. Their next mission is to work out why, and so unlock more of the secrets of this stunning phenomenon. Their next rocket is almost ready for launch. So this is it, huh? This is the scientific payload. This is what's going to do all your measurements of the aurora.
Exactly, it's a scientific payload.
So how long does it have in the center of the aurora to take all its measurements?
A minute, a few minutes, that's all.
Once airborne, it's critical that the rocket gathers as much information as possible, as quickly as possible. Once it reaches an altitude of 75 kilometers, the nose cone will open and the instruments will begin to take measurements.
Okay, on each of these 4 tips of this umbrella, we have these needle probes. And these look like, what's it called in English? Acupuncture?
Yeah, acupuncture needles.
Yes.
I love that description.
These things are going to measure how the situation up there in space is.
How the aurorae work. The needles will detect the temperature and electrical charge of the particles creating the patterns of light. This information will then be transmitted back to the control center, ready to be analyzed by the team. But in the end, the success of this mission will depend on the perfect launch.
There are a lot of things happening around the scientist. The scientist can't do anything anymore. He can just say, yes, go, and he can say stop until the last second.
And when that moment comes, everyone crosses their fingers. Have you ever missed the aurora, though?
No, I cannot remember.
We're not quite as close as those rockets to the Aurora Borealis, but at 32,000 feet, we're not doing too badly, and it's still shining there in its beautiful green hue outside our window. It's really a sight for sore eyes. Pete, we were talking in Andoya there about how the electrons in Aurora, like the one we're looking at, travel in incredibly narrow bands, but then this Aurora is part of a bigger picture, if you will, a part of a bigger area that's a bit of a circular shape over the poles.
That's right. I mean, it's down to the shape of the Earth's magnetic field, which funnels the electrons down towards the north magnetic pole and the south magnetic pole. So as they go through the atmosphere around those poles, they form a ring of glowing light around them.
Loving your demo with your glow stick there. So it's basically a circular shape where the aurora can appear. Is it a perfect circle?
No, the Earth's magnetic field, if the Earth was left to its own devices, it would be symmetrical around the Earth. But the solar wind squashes the magnetic field towards the surface of the Earth on the day side and elongates it away from the Earth on the night side. In fact, it goes way beyond the orbit of the Moon. And that has an effect on this shape, the shape of this glowing ring, and it pushes it towards the magnetic pole on the day side and elongates it away on the night side. So it's not a circle, it's an oval.
Oh, right, okay, so it's known as the auroral oval,
Absolutely
isn't it?
right,
so
yeah.
does that mean that this here is part of this oval circling, you know, making a circle around the magnetic pole?
Yeah.
I mean, you can almost see sometimes in the arc the shape over the globe, can't
That's
you,
right, you
from
can
this
imagine
altitude?
it like a crown going around the top of the Earth.
It's very beautiful. And the aurora from last night at ASCAT actually inspired some of our viewers to write in some questions. Can I pose them to you?
Yeah, of course.
Being our expert on our flight, Pete. 13-year-old Ellie asked, could the aurora be used as an energy source?
What a fantastic question.
Isn't it?
Well, a really energetic auroral display could probably power the whole of the UK.
Yeah.
But the problem is getting up there to actually get at that energy, and because the aurora is enormous. We haven't got the technology to do that yet.
Might that happen in the future? Might we have the technology?
I don't know. I would really hope so.
The
Solve
beauty
a
of
lot of
science.
problems, wouldn't it?
It really would. What about Stefan Novak? He's asking, what is the rarest colour of aurorae and why? That's a very good question too.
Okay, well, the most common colour is green, and then sort of a reddy brown, which is on top of the green. Then the next one would be a sort of pinky band at the bottom of the green.
Okay.
But the holy grail for aurora photographers are the sort of blues and purples, which appear in these huge ray structures which go up.
Why are they so rare?
Well, you need a really energetic display to see those.
Okay, so far we're seeing green at our window.
Yeah.
No red on the top quite yet.
Not yet.
But you know, anything can happen at any point. That's the beauty of auroral hunting. So come back to us very soon. Back to you guys at Jodrell.
Thank you very much, Liz. Now, it's a very complex phenomenon in nature, but we can show you how the aurora forms during very clearly with this contraption, we're going to create an aurora in a jar. This is based on the apparatus used by the Norwegian scientist Christian Birkeland, who was the first to work out what causes aurorae. So what's going on here?
Yeah, this is a beautiful demonstration. Essentially, the big ball is representing the sun, the small ball is representing the Earth. Both of them are electrically charged, and the Earth ball has got a magnetic field in it which is similar to the Earth's magnetic field. So imagine those field lines that we've been talking about. They run in a shape from one pole down to the other pole. And what you're seeing is, because there's an electric charge on these balls, there are electrons streaming off the sun, the big ball, streaming towards the Earth, the smaller ball, and then coming down the magnetic field lines onto the pole. Now, this is, you can hear a hum there, that's a vacuum pump. So some of the air has been pumped out of this to allow the electrons to make it across that gap, but not all. There's nitrogen in here, a lot of nitrogen. And this is what Pete was referring to. He was talking about the holy grail for aurora photographers, which is this purple glow. That's what we're seeing. So this isn't a simulation, really. It's the same physics as the aurora. It's electrons travelling down the magnetic field lines, hitting the nitrogen molecules inside here, in the atmosphere, and promoting electrons up. They're dropping back, emitting this purple glow.
We have a question here from Timothy Newry. It says, how do aurorae differ on different planets in the universe, and what would you see if you were there?
Well, they'll differ. The composition of the atmosphere is different. The colours are characteristic of the molecules and atoms in the atmosphere. As I said, this purple is nitrogen. But the physics is the same everywhere in the universe. So the process is the same. If you have a nitrogen atmosphere anywhere in the universe, you'll get this purple glow from the aurora.
OK, grand. So in other words, the aurora is the same whether it's on Venus, whether it's on here, whether it's in this jar. Oh. The physics of the universe is the same process.
That's what I like about this. And actually, this was first done, by the way, in 1895. That's before the discovery of the electron. So it was very difficult to understand what was happening. And these are the kind of models that allowed physicists to tease out the processes that cause the aurora.
Now, as we said, we believe there is a very good chance that we'll be able to see an aurora across a lot of the UK and Ireland tonight that'll come down that far south. We want you to take photographs, but just to give you a clear idea of where it might be most possible, let's check the weather forecast.
Hi there, Dara, thanks. Very exciting news, of course, that we've had more solar activity, which is likely to give us an enhanced chance of seeing the beautiful aurora borealis in the next 24 to 36 hours. And because it was more potent than last night's, there's a chance even here in the UK, but we need the weather to play ball as well. So what about through this evening and overnight? Unfortunately, more unwelcome rain for many, but for you stargazers, hopefully we'll keep some clear skies to parts of northwest Northern Ireland, Scotland, and later as the rain clears in the south. But do watch out for some fog in the north, actually. Might not be having high-level cloud, but instead low-level cloud. But come tomorrow, when there's an even better chance of seeing that aurora borealis, it looks as if the weather will play ball, and it looks as if the skies will start to clear as we have a ridge of high pressure in. The only downside is it will be colder if you're heading out tomorrow night, but it looks as if the cloud will start to melt away. So I'd say there's a good chance in many parts, obviously a better chance the further north you are in the UK of seeing the aurora borealis, but for other stargazing, it's a pretty good night. It's just going to be cold.
Now, in 1961, President John F. Kennedy pledged to land men on the moon and bring them back safely to Earth by the end of the decade. This rocket took off just 7 years later, the first Apollo craft to carry a crew into space. Here they are, the pioneering astronauts who made the moon landings in 1969 possible, and one of them is here with us in the studio now. It's Colonel Walt Cunningham. Thank you for joining us, Walt.
It's my pleasure to be here.
The first question must be, what inspired you to become an astronaut? Because you must have made the decision before the space race began.
Well, I don't know about the astronaut part, but when I grew up, the only thing I can ever remember wanting to be when I was a kid was a fighter pilot. And out of high school, I ended up becoming a Marine Corps fighter pilot, ended up going back to college. And while I was in college, of course, they had the Mercury astronauts, and I remember following them and envying them, of course. But I'll never forget May 5th, 1961. It was early in the morning. I was driving to work. I was working while I was going to college. And I had to stop. It was a little before 7 to get to work early. A little before 7 in California. A little before 10 out in Florida. And I was listening to the countdown for the first Mercury flight, Alan Shepard. It got down to the last couple of minutes, and I had to pull over beside the road. I was up on a mountain. Pull over beside the road and listen. And when I got down, I remember 5, 4, 3, 2, 1, liftoff. And I heard a voice screaming around me, and it said, "You lucky son of a bitch." And I looked around because I realized it was me doing the screaming. And at the time, I was terribly impressed. Later, I realized that was when I decided, boy, this is the way I'm going to do it. Higher, farther, faster. That's all I ever wanted to do. Yeah. Higher, farther, faster.
And tell me, what actually was the mission profile of Apollo 7? What did you have to achieve on that mission?
Well, of course, we had 5 flights planned to land on the moon, if everything went perfect. And of course, we'd already had the Apollo 1 fire, and we'd lost 1 crew. And we were busy just trying to test the spacecraft. So everything in the spacecraft that we'd been working with at the contractors for years, as a matter of fact, we had to test all those systems. And some of the most important ones, of course, is to have...
this is your launch, eh?
Yeah, that is. I didn't see it from this perspective, but we were enjoying it, actually. We were enjoying the ride.
I must say, what does it feel like being sat there at this point?
Well,
the first test flight of this vehicle, first manned.
Yes, it was. And it was, the vibration was something you felt, but we couldn't hear anything. We were out faster than the speed of sound pretty quickly, and we're out ahead of it. And the Gs, well, they were more than they are today in what they do. A lot of things have changed from the program then to the program now. But our job was to test everything in the spacecraft, because if we had a really good flight, then we were going to let Apollo 8 go around the moon. Yeah. If we'd had a problem, Apollo 8 would not have gone.
And you went into orbit and then stayed in orbit for how long?
We were up there for 11 days. Yeah.
And how did it perform? I mean, the first flight of the new vehicle.
Well, following the first attempt, which was Apollo 1, the vehicle was not really all that good, and we knew it, and we thought we could compensate for it with our own skills. But when they fixed everything that could possibly have caused the fire, and a lot of things that we wanted operationally installed in the spacecraft, when we flew it, I have to tell you, it was amazing. I mean, it really was. It was the longest, most ambitious, most successful first test flight of any new machine. It was almost perfect, as a matter of fact.
And it's interesting that when you look at the timeline, it's astonishing, certainly from a modern perspective, that you flew October 1968. A month and a half or 2 months later, Apollo 8 goes around the back of the moon, you test the LEM, and then you go land on the moon in July 69. So what was it like being involved in such a program, this national goal? We are going to go there. By 1970, we will have landed.
Well, we had a mission scheduled every 2 months. If everything went perfect, that was the way it was going to work out. I would say that we did not expect it to be that perfect. I mean, there was not a problem, there was not a delay, and everybody was committed. It wasn't just the crew. You know, we got the notoriety and the attention, but it was really the commitment from the engineering, from the mission control people and management's decisions. We had an attitude that said the job has got to get done. And so everybody followed through on that.
And I must ask, what kind of people are you? Because if you look at the Apollo program, look at Apollo 13. Well, you know, Apollo 11 lands on the moon. Apollo 12 is struck by lightning just after liftoff. I know a lot of systems failed, got it into orbit, fixed it, went to the moon. Apollo 13, famously problems. What does it take to be an astronaut flying these vehicles, these experimental vehicles?
Well, it's interesting because the public is what's changed the most. The guys at the time were all committed. But by Apollo 13, they weren't even really covering the flight live. Yeah. And I was at home at the time, and I can remember when they announced that Apollo 13 had a problem. And I lived right across the street from the mission control. So I can remember going over there, listening. I was in mission control, right behind, and I was listening to what was going on board. And Jack Swigert, who had been on our support crew, and Jack and I and another mission controller, we had developed the malfunction procedures on the spacecraft, all of them. And when I was there, I listened. I could listen and go through it. Jack Swigert had done everything you could possibly do. I wasn't there but 10 minutes and went home and went to bed.
Relaxed that everything had
Well, I didn't know how the outcome was, but I know that they'd done everything they could possibly have done because we'd worked out the procedures.
We've lots of questions coming in from viewers. Andy Kendrick asked, what stresses did you feel on your body on takeoff?
Well, I think we got up to a little over 5 Gs at the time, but you know, it goes through that fairly quickly. It's the first 2 minutes when you got the main stage accelerating. When you get up to 2.5 minutes and you're separated, from that time on, it's a fairly easy ride up there.
And Fiona Wright asked, what did you experience emotionally in orbit, in space?
Emotionally? Well, mostly it was just pleased and satisfaction that we're here now. And we were still committed and determined that if this mission fails, it isn't going to fail because of me. We all had that same attitude, and we just were trying to do perfection.
Fantastic. Now, the ultimate aim of the Apollo mission is obviously to get to the moon. The moon remains one of the most exciting things for you to look at through a telescope even, but it has its own difficulties technically in doing that. Here's Mark with a quick guide.
Well, I'm afraid we've still got rain here at Jodrell Bank, but take a look at this glorious view we got of the moon yesterday from Norfolk. You can see some of the lunar detail beautifully. Now, the moon is a really helpful subject if you're starting out in astronomy, because even with a normal telescope, you get a great view like this one that we got through one of our telescopes yesterday. You can see it actually bobbling around quite a bit, and that's from the wind that we're experiencing. But we see it because it reflects sunlight, but it's sometimes too bright to see comfortably through a telescope. But in order to pick out its small details, you may need one of these. Now, this is a moon filter, and you fit it to the eyepiece of a telescope, and it simply cuts down the brightness of the moon so you can view it in much more comfort. Now, of course, last month, the Chinese lander Chang'e 3 became the first craft to land on the moon for 40 years. There's its landing site in Mare Imbrium. You can see a larger image just showing you there near the craters to the north of the plane. There's also a wonderful image of the Jade Rabbit, which is the rover which is trundling around the surface. You can see the solar panels, the radio dish, and, of course, the tracks as it runs around the surface. But for now, it's back to Brian and Dara in the studio.
Thank you very, very much, Mark. Now, Walt will be with us, of course, later. Walt has left. Walt will be with us for Back to Earth after this show for more questions from us and from yourselves. But now we're going immediately back to Liz to see how the Aurora show is going.
Thanks very much, Dara. Can I just say, every time we're off air, our pilots are doing so well, banking like the clappers to get us back into the trajectory that could give you these images of the Aurora. Look at that structure, look at that green glow. It is such a treat to be up here above the cloud cover, getting a load of that Aurora Borealis. And, you know, Pete and I were discussing how it is difficult to predict Aurora. Solar activity is definitely very useful, but we have a few other tools at our disposal, don't we, to make sure that we can catch these when and as they appear. I mean, for example, Pete, is it possible to know geographically, where is that light going to appear next?
Yes, it is. There's a value. It's called the KP index, which goes from 0 to 9, which basically gives you an idea of how far south the auroral oval will stretch.
Right.
Now, for Toronto, this one here that we've got tonight is so beautiful to look at. It's probably about KP1. It's right over the top of us. But
and you were looking at that. You were saying KP1, KP2 as we were getting
tonight,
on the plane, and there it is in all its glory.
That's right. But if the numbers go up, say 8 to 9, because it runs from 0 to 9, then that would be an aurora which may be visible from the south of England, for example.
Okay, and they're rarer, of course, but they can
rarer.
happen as well.
Yeah.
So say, for example, you know, the sun's been really, really active. I know my KP is geographically perfect for where I'm standing. Is that it? Am I guaranteed an aurora, or is it more complicated than that?
But there are other things which actually come into play as well, and a very important one is the magnetic polarity of the stuff coming from the sun, because the Earth has a magnetic field around it, which has a north-pointing field. Now, if the stuff coming from the sun is a north-pointing field as well, it doesn't connect up with us, and not much goes on. But if the stuff coming from the sun has a south-pointing field, then it can connect with the Earth's magnetic field, and the aurora magic can occur.
Okay, so that's quite a crucial factor as well. Plays a very big role. You know what? We have been treated to this beautiful light show. I can't get enough of this. I actually don't want the plane to land. We hopefully will have enough fuel for us to circle a few more times and fill our boots with this wonderful sight. But what's really interesting, and I think Dara and Brian have been mentioning in Jodrell earlier on, is that something very exciting has been happening with our sun. Okay, an event that's created this coronal mass ejection that's heading our way potentially tomorrow. What does it mean for us? How could that change our view from this plane tomorrow when we fly?
It could completely change it utterly. That stuff's heading towards us at a speed of about 8.6 million kilometres per hour, which is astonishing. And that's going to slam into the Earth's magnetic field at estimated about 8 o'clock tomorrow morning. And that could kick off a geomagnetic storm, which could trigger a really good aurora. But we must say it could go the other way as well, so no guarantees yet.
So it's still not an exact science, guys. The colours may change from these greens we're looking at now to reds and to purples and to blues. We just simply won't know until very close to when we take off. But if the stars are aligned, if all of those factors, all of those predicting tools are right, we may give you the best light show on Earth. But for now, we're going to leave you with these images, and loath as I am to say it, we're going to say goodnight for tonight. See you tomorrow.
Good night. Good night. They're incredible because you can actually see it dynamically. The system's changing. You can see the different structures appearing and disappearing.
You can see those curtains there as the aurora develops, and so I think they're probably going to get some great pictures actually as the flight develops, and we're going to miss them.
I know.
We'll get them tomorrow.
We'll get them tomorrow. Now, don't forget that we need your help again this year in our challenge to find distant hidden galaxies. We've already had over 4 million hits, and it's looking very promising. But we need more of you to go online and take part.
Yeah, if you want to try your hand at making an astronomical discovery for yourself, make sure you visit our website and follow the link to Finding Hidden Galaxies. And tomorrow night we'll bring you the results. But I just to say, if I look at the Hubble telescope now, it's turned. It's pointing away from the control room. It's not our usual angle, and that's because it's gone to look at a very interesting candidate that someone out there pointed out and discovered. Do some more physics, do some radio astronomy to try and characterise it. So we're getting real science out of this, so it's really worth going. And I think the website's been changed as well to get some of the prime candidates there to get a second look. So go there. Well worth it.
We're asking you to discover distant galaxies, but is there any realistic chance that we could one day journey to the stars?
To reach the speeds needed for interstellar travel, we need a starship with an engine fit for the job. An almighty rocket engine. Everything you need to know about rockets is contained in one very simple equation, which is known, perhaps unsurprisingly, as the rocket equation. It says that the velocity of your rocket, the speed you want to get it flying, depends basically on only 2 things. One is something called the mass ratio, and then there's this term, the exhaust velocity. That's the speed that you throw the stuff out of the back. And that depends essentially on only one thing, which is the kind of fuel you use. Today's most advanced rockets are powered by chemical fuels, the stuff that got us to the moon. This one is being tested for a future mission to Mars, and its exhaust can reach around 4,500 miles per hour. But that could never get us to the stars, so scientists have long searched for an alternative. In 1945, the power within the atom was unleashed. And soon afterwards, a group of scientists joined forces in complete secrecy to work on Project Orion, a mission to see if atomic bombs could be used to propel rockets into space. These are some of the unclassified designs from Project Orion, and you see that they are really ambitious. The famous physicist Freeman Dyson worked on this project for a while, and he published some estimates as to what it would take to launch a 100,000-ton spacecraft to around 3% the speed of light. So the kind of speed you would need to send a spacecraft out to the nearby stars. But despite some impressive test launches, this Starship would need 300,000 atomic bombs to reach that speed. This was never going to be a solution. But there is another substance that has the potential to be an even more powerful rocket fuel. Everything we can see in the universe, every star, every planet, every galaxy, you, me, this rock, is made of matter, a collection of subatomic particles. But we now know that all those particles have partners, same mass, opposite electric charge, which are called antiparticles or antimatter. Now, antimatter has the property that if you bring it into contact with matter, they can annihilate into pure energy. All their mass is carried away, ultimately, by a stream of photons travelling at the speed of light. So, antimatter provides the ideal rocket fuel. The hard bit is building a fuel tank that can store it. But at one of the largest antimatter factories in the world, they're doing just that.
Matter and antimatter can't exist together, they annihilate. So the whole trick is to keep the antimatter away from the matter.
After making antimatter in particle accelerators, researchers at CERN are constructing tanks that can hold the antimatter without it annihilating.
So we have very high vacuum, all the gas has been removed, and we make sort of electromagnetic bottles, force fields that hold the antimatter away from the matter.
And in 2010, they succeeded in bottling atoms of antimatter in this tank for the very first time.
The concept of antimatter as a rocket fuel is spot on, right? It has the highest energy to mass ratio of anything that you could imagine.
So far, they've only managed to hold it for around 16 minutes. But it does mean that the idea of an antimatter starship is one step closer to reality. And perhaps one day, we could be using it to power our way to the stars. Well, Commander Chris Hadfield is with us again. Chris, so there's a future there. It's almost a little bit of a disappointing view of the future. We haven't built starships yet. We have, of course, built the International Space Station, which you commanded. So are you content or happy or disappointed with where we are now in terms of manned or human space exploration?
I think it's going, as we've explored the whole surface of the world for the last 50,000 years, it's sort of at that pace. We make some inventions, we get as far as we can, and then we test that new area. And the space station is testing what you make the hull out of and how you make the systems inside. We've had troubles with the cooling system. We're learning. It's like sailing a ship up and down within sight of land before you head across the ocean. And we need to figure all that out. And a lot of it can't be tested on the surface. So it's not a race. We're not in a gigantic hurry to do it. And we want to make sure we make the inventions as time goes on. So actually, I'm heartened by it. We are learning as we go. Our probes, as you've shown at the outset, are actually outside the effect of our sun right now. And we will incrementally continue to move as far as our technology can take us.
Would it help if we were in a race? Do you think we need that imperative, that moonshot call?
The trouble with races are, as soon as you cross the finish line, it's over. In the stage we're at right now is an incremental expansion where we have taken that first permanent step away from the Earth. The space station is our first permanent international outpost away from the world, and we need to learn a lot there before we look for the next lily pad as we work our way across.
It's a big structure, isn't it? It's not to minimise the achievement of the space station. I think you said to me earlier, it's bigger than I thought it was.
Yeah, you can work all day and not see your other crew members. I mean, it's a big, busy laboratory with a couple hundred experiments on board, an amazing viewport for the world, a place to look out at the universe, and in fact, with the alpha magnetic spectrometer to collect the subatomic subatomic particles of the universe, a huge test bed as we're laying the groundwork that'll allow us to go further in the future.
I'm so glad you got some particle physics in there. But Chris, we're going to hear more of that in Back to Earth a little later on. But thanks for now.
Thank you.
Chris and Walt will be joining us in a couple of minutes as this finishes. Tomorrow night, though, we've news of a brand new mission to map the Milky Way called Gaia. And I'll be finding out what a journey to another star might feel like. It turns out it feels like putting on about 40 stone.
So just like Christmas.
Basically. If there's anything you want to ask about the Milky Way or galactic travel, send us your questions now.
Well, stay with us because our astronauts Walt and Chris will be answering lots more questions right after this show when we're back to Earth here on BBC Two. So we'll see you in about, 2 minutes?
2 minutes.
See ya.